All right, chemical reactions. Let's make stuff from other stuff. Let's do it. Our first reaction actually was acidity, so maybe this is the second or third reaction. But it's the first reaction that's not just trading a proton back and forth. We're going to dig into this reaction. I'm going to explain kind of what this language means, and then we're going to really get into every detail of this reaction because it's an archetype of a lot of reactions that are going to work like this. Okay, so let's start here. You might notice that it looks a little bit different than chemical reactions that you're used to seeing in chemistry 115 and 116. For starters, it's not really balanced. I didn't draw everything out on the arrow, or on both sides of the arrow. And notice that I've got a bunch of stuff above and below this arrow. So my chloromethane and my sodium hydroxide I would call reactants or reagents. And I'm not super interested in the distinction between the two right now. You might think of NaOH as a reagent just because I'm sort of adding it to something else to make it go. But as far as I'm concerned, we can call both of these either of these, and that's okay. This is our product, methanol. It's a pretty cheap product. This is not going to buy us a boat, more than likely. A lot of times we'll be talking about the solvent that we are doing this in. So could we do this without a solvent, just in neat chloromethane? Well, maybe. I think chloromethane might be a gas, so that might not work so well. But in general, we're going to probably have something, usually under the arrow, but sometimes on top, something there more often than not. And sometimes it's something that we really want to cue in on as being important, but most of the time, it's not the first thing that we are looking at. For this kind of reaction, acetone is a pretty good solvent. Acetone is nail polish remover. It's a ketone. It's the simplest ketone. We haven't learned ketone nomenclature yet, but here you go. Your first ketone that you should know how to name is acetone, with just a methyl group on either side of the CO double bond. Okay, so again, this is how we're going to write out equations. Sometimes you'll see an equilibrium arrow in the middle if it's going back and forth. In this case, it is not going back and forth. It is pretty much irreversible. I'm not really going to care between sort of which reagent or reactant is in front of versus on top of the arrow. And I'm also not going to even draw a huge distinction between what's on top of the arrow or what's below the arrow. Okay? My biggest distinction I'm drawing here is before, after, right? Reactants, products. Let's talk about reaction mechanisms. This is something that I care a lot about, especially in my training in graduate school. Mechanisms refers to simply how the reaction happens, like physically, what is happening. If you were to describe to me what has to happen in this reaction, going from chloromethane to methanol, what would you say has to happen? Well, you'd say I need to break a carbon-chlorine bond, and then I need to make a CO bond. This bond is going to be broken, and this CO bond is going to be formed at the same time. Okay, so let's draw this. So here I've got my chloromethane. I've drawn out this bond because I'm going to break it, and I want to call attention to it. And here is my OH minus, right? It's got a full charge. It's probably a little bit unstable and high energy, so it wants to go and make a bond. Let's bring in some nomenclature. I'm going to call hydroxide a nucleophile. Nucleophiles are electron-rich species. They've got electrons. They want to go use them to go make a bond. We can also think of this as a Lewis base. If you remember different definitions of acids and bases, we said that we usually talk about Bronsted acids, proton donors, and Bronsted bases, proton acceptors. In the Lewis sense, we're talking about electrons. Lewis bases donate electrons because they're electron-rich. Lewis acids accept electrons because they're electron-poor. Here, we're going to use the word electrophile in place of Lewis acid, but they essentially mean the same thing. The idea here is that this wants electrons because this wants to break this bond and give this chlorine extra electrons. Another way to think about it is that this chlorine is pulling electrons away from carbon, And so carbon is a little electron poor. So now we're going to use arrows, and we're going to use them kind of properly for the first time. We used arrows to talk about resonance structures, about delocalization. And there I always caution that, when we draw these arrows, it's not really electrons moving back and forth. When we use arrows to describe a reaction mechanism, we absolutely are describing electron movement. So here, my arrow starts at my negative charge. My arrow always starts at my nucleophile, where the electrons are. And I'm going to draw the arrow to where they are going. I am making a bond to carbon. So the arrow ends at carbon. It's a double-headed arrow because I am moving 2 electrons. We won't use single-headed fishhook-like arrows until organic 2. So, okay, what this arrow denotes is that I'm making a new bond. I'm making a new bond between oxygen and carbon. But to do that, and not give carbon that dreaded 5th bond, at the same time, I need to break that bond. So here are my products. My products are methanol and chloride. Now, chloride has that extra negative charge. I broke that carbon-chlorine bond and put those electrons onto the chlorine. If I put in lone pairs, now my chloride has an octet, and that's why it's pretty stable. So again, in this reaction, I'm making a new carbon-oxygen bond. I am breaking a carbon-chlorine bond. These electrons in the negative charge become a new bond. These electrons in the bond become a new charge. We're going to call this chlorine a leaving group because it is leaving. It is leaving the molecule, it is becoming chloride and going away. And one thing we'll talk about at length in a bit is that these reactions require a good leaving group. A good leaving group is something that's relatively stable on its own. Okay, so again, verbiage. The thing with the extra electrons we're going to call the nucleophile. It's also a Lewis base. The thing that's getting attacked, and we do call this nucleophilic attack, the thing that's getting attacked is the electrophile. It's electron poor. We might also call it a Lewis acid. These arrows denote electron movement. Start where the electrons are, end where they are going. Here, I'm starting in the middle of the bond, which means I'm going to break that bond, and the electrons go on to chlorine to make chloride. And here's my products, my methanol and my methanol product and my leaving group chloride. When you care about reaction mechanisms, you really care about potential energy surfaces. So here is the potential energy surface for this reaction. Again, my y-axis here is just potential energy. I am starting up here and ending up down here. This is an exothermic reaction. How can I justify that? Well, which is the stronger base between OH minus and chloride? Right? OH minus is quite a bit stronger base than chloride. How do I know that? Well, think about the conjugate acids. Water, HCl. Right? HCl is a very strong acid. Cl minus is a very weak base. And again, when we say weak, we mean stable. Weak, stable, low potential energy. These are all kind of synonyms. And so this is a very exothermic reaction. So this is also going in one step. Like I said, we're not breaking a bond first and then forming it, or vice versa. We're doing everything together. So how does that actually look? So we should think about it like this. I am slowly breaking the CCl bond. The CCl bond is getting longer. My distance between oxygen and carbon is getting shorter. So I'm not guaranteeing that these distances are exactly the same in this top of the hill transition state, but I am saying that this is not quite formed and that is not quite broken. Okay? So this is all happening at once. I call this a bimolecular transition state because I've got 2 molecules involved, my hydroxide and my chloromethane. So because they're both involved, this is going to be a bimolecular transition state. And again, transition state is always the highest energy peak I have to go through to get from my reagents reactants to my products. Remember 116? Remember how fun that is? Maybe with me, maybe with somebody else, but maybe with me. So we talked a lot about potential energy surfaces, and we talked about them in terms of kinetics versus thermodynamics. So kinetics is asking how big is that barrier? Kinetics asks how much energy do I need to get from where I'm starting to get over the hill, over the transition state, to go over to products, right? So in terms of rate, it actually doesn't matter how deep this product is. I can only see what's in front of me. We call that distance in energy between my reagents and my transition state either the activation energy, EA, that's what we usually said in 116. I sometimes call it delta G double dagger, because this double dagger signifier usually denotes something to do with transition states. But for now, we can basically treat those as more or less the same. Alison Fleischman will correct you if you confuse them when you get to Chem 370. But for now, they are both a measure of how big this barrier is. And again, that governs how fast these reactions happen. If we look at the distance between our reactants and our products in terms of energy, that's delta G naught. That is the energy of reaction, right? The free energy of reaction. And what that is going to tell us is what is there more of at equilibrium. If this has enough energy to go back and forth pretty rapidly, then this is really useful because it tells us that, okay, most of it will end up down here. But in some reactions, this distance is so big, and more to the point, the barrier height that our products see to get over the hill is so big that we're never going to get to equilibrium, right? So burning paper, I'm not going to see ash ever go back to paper because that energy drop is just too great to get back up the hill. So again, two things we're wondering about. We're wondering about my activation energy, my barrier height. That's going to dictate rate. And then if I'm at equilibrium, I might care about the difference between the two energies here. So in the grand classification of reactions, we're going to call this an SN2 reaction. It is a nucleophilic substitution. Here is our nucleophile. It is substituting for the chlorine, so it's a substitution by a nucleophile. And it's bimolecular because there are two molecules involved in the rate determining step, which is the only step here. It's one-step reaction. So one-step reaction means that both molecules are involved. Nucleophilic substitution bimolecular. SN2, typically big S, big N, but subscript, and a 2, normal size 2. This is an archetypal reaction. There are lots and lots of reactions that fall under this general umbrella, and I would say it is the most important archetypal classification of reactions, which is why I'm covering it first. And this is a bit about the only reaction, almost the only reaction I'm going to cover until the second midterm. And so we're going to really first-year studies style close read this reaction and think about what are all the differences and tweaks we could make to this reaction and what effect would it have. So for instance, what is nucleophilicity? And how important is that to this reaction? And how can I think of good nucleophiles versus bad nucleophiles? And later on, this is going to be very important, but we'll want to talk about nucleophilicity versus basicity. Often, they're the same. So many good bases are also good nucleophiles. But there are some nucleophiles that are not so basic, and there are some bases that are not so nucleophilic. And so that's what I'm going to talk about first. Then we'll talk about how the electrophile structure really is important to the rate of this reaction. This is a fast one, but if I were to have tert-butyl chloride, it would be so slow that it wouldn't basically happen ever. And so we'll talk about why that might be. And these arrows kind of give you a sense maybe of why that might be. We'll talk about how the leaving group is important. You're going to need a good leaving group for this, something that is willing to leave and is pretty stable on its own. So to spoil it a little bit, our most popular leaving groups are going to be the halides. Chloride, fluoride, bromide, chloride, bromide, iodide, not fluoride. but there are others. And I do want to talk about what the body uses for its leaving groups, because many times the body is not using chloride or bromide or iodide as an SN2 leaving group. I do want to talk about solvent. Again, this is something that sometimes we pay a little bit too much attention to, but solvent choice is going to factor in to this and other reactions. And finally, I want to talk about stereochemistry. So we just learned about chirality in this class. And so how does this affect chirality? That's not chiral, but what if it were? If it were, would that chirality be preserved? Would I know the chirality of my product, or would I get a racemic 50-50 mixture? We'll talk about that too. The first thing we're going to talk about is nucleophilicity versus basicity. When are they the same and when are they different?